All right, we're recording now. Are there any questions? Let's see in the comment and chat. Yeah, we're gonna continue with what we are doing, and first we're gonna take a look at let's erase this. That's stupid. All right, just a second. We're gonna look at this is section 5.3, perturbed systems. Okay. So before we looked at x prime equal ATX. Now we're going to look at x prime equal ATX plus BTX. So A and B are n by n continuous matrices on some interval I. All right. So here, BT is like a noise matrix. So and this is 5.31. This is for t bigger or equal to 0. This is 5.3.2. All right. So from the stability of 5.3.1, we want to obtain stability info about the perturbed system 5.32. Okay, so basically by looking at the magnitude of BT. Of course, we're gonna everything depend on how big is B is. All right. Okay. So take a look at it and see what we're up to here for a second. All right. So you see the setup, and we're gonna have, and we're gonna assume here xt naught equals some x naught, of course. All right. And we're going to have our first theorem. All right. So this is theorem 5.31. Says assume the zero solution of 5.3.1 is uniformly stable. Okay. If for some positive constant E, 0 to infinity, b of t dt less or equal to E, this is 5.3.3, then the zero solution, that means x equals 0, of 5.3.2 is uniformly stable. So again, as you see, we assumed the zero solution of the homogeneous equation is uniformly stable. And then if we put this kind of magnitude and on B, then we have uniform stability for that matrix, for that equation. Note that condition 5.3.3 means BT is integrable. Okay, that means the value of its integral based on the norm is constant. I mean, is constant. Any questions? All right, here's the proof. Let phi of t be the fundamental matrix of 5.3.1. Since the zero solution of 5.3.1 is uniformly stable, there is a positive constant K, so that phi of t by inverse of S less or equal to K. This is what it means. This is by a previous theorem. Okay? All right. Now, by the variation of the parameter formula, and this is, I'll give you the number of it, 3.34, the solution of 5.3.2 is x of t equal phi t, phi inverse of t naught, x naught, plus t naught to t, phi of t, phi inverse of s, bs, xs, ds. Okay?
Can I ask
Now,
there, please?
huh?
May I ask a question there, please?
Sure.
Okay, so what you wrote on the board makes sense. I'm looking at the book. It doesn't have an
There is an
equation.
XS missing.
Okay, perfect. That's what I wanted to know.
Yes, an XS missing. This is one of the heartbroken mistakes, okay? Breaking mistake.
Perfect. Thanks.
Yeah. But the proof is correct. The proof is fine because for some reason later on, it's included, okay? So does everything make sense to you now?
Yep, it does.
All right. So you see we are using everything we have built before, right? Everything we talked about before, we are using over and over. So it's not a joke. It's not like we're jumping from one topic to other. They all follow each other. All right. So I'm going to continue here. Then xt less or equal to phi t, phi inverse of t naught, x naught plus t naught to t, phi t, phi inverse of s, bs, x of s, ds. Okay? We're going to take the absolute value, the norm. All right? So this is less or equal to kx naught plus k t naught to t bs x of s ds. Okay? What do you think I am going to use now to get a bound on x? What do you think I'm going to use? You can say it even if you read it in the book. What am I going to use? Gronwall's inequality. So this is less or equal to k x naught e to the t naught to t k bs ds, and this is less or equal to k x naught, and this is e to the 0 to infinity k bs ds, and this is less or equal to k x naught e to the k e. Remember? Remember what this is? Okay. Now, for any epsilon positive, we need to find delta positive so that if x naught less than delta implies x which is less or equal to k x naught e to the k e, which is less or equal to k delta e to the k e, and this is equal to epsilon if I take delta is delta is epsilon over k e to the k. That's it. Just complete the proof. Okay. All right. Questions? What do you think? It's a very neat proof, isn't it? Take a look at it. See if you have any questions before I move on to an example. All right. So let's take a look at an example. Okay. So let's take a look at example 5.2. Let's say we have x second plus x equals 0. Okay. All right. If I let x1 equal to x and x2 equal x1 the prime, this means is that what I want? X1 equal to x2. Okay. Yeah. Then x2 prime equal to, let's see. x1 second, that is x second, that is minus x, that is minus x1. So the system we have x1 okay, x2 prime, x1 equal to x1 prime equal to x prime, which is x2. All right, so x1 prime equal to x2. Why did I? Yeah, x1 prime equal to x2. Okay, I can do it differently. What I did in the book is fine. I'm trying to explain it to you in a better way. How did we do the change of variables? So we let x1 equal to x, x2 prime equal to x1. Okay, so let me check something here. I mean, I know we've done this many, many times, and all of a sudden I went blank. I don't know why I do that all the time. Okay. So we're gonna do so we usually let as I said, x1 equal to x and x2 equal to x prime. Sorry about that. Okay. And so x1 prime equal to x prime equal to x2 and x2 prime equal x second equal minus x. That is minus x1. So we have x1 prime is x2, x2 prime is minus x1. So I can write this as x equal to 0, 1, minus 1, 0, x1, x2. So this is our A. Okay? And we shall see that the eigenvalues, lambda, we have lambda square plus 1 equals 0, lambda equal plus or minus r. So that means by one of the theorem, its zero solution is uniformly stable. All right? Because the eigenvalues have zero real part, then you get uniform stability. All right. So now, in the next example, we perturb x second plus x equals 0 by adding a small term 2 over tx prime. So we're going to look at this is example. That is, no, I'm staying in the same example. And this one, this is theorem 5.3.1, where the result comes from. So now, we're gonna consider x second minus 2 over t x prime plus x equals 0 for t is positive. So as you see, the velocity here, v prime, is basically, we're adding very small perturbed noise to the equation. So let's see how this is gonna affect the problem. Why don't you go ahead and use this transformation again? Use this transformation to write this one in terms of a matrix. Go ahead, take a few minutes. All right, so if we do this, and we're looking at this equation now. So x1 equal x, x2 equal x prime, x1 prime equal x prime equal x2, x2 prime equal x second. That is 2 over t x prime minus x. That is, what is x? X is x1, so it's minus x1 plus 2 over t. X prime is x2. So notice how I am going to write this. I'm going to write it as, so I'm gonna write it as 0, 1, minus 1, 0 times x1, x2 plus 0, 0 minus 1, 2 x1, x2. Okay, it's x1, x1, x1 prime equal to x1 prime equal to x2, and x2 prime equal to minus x1 plus 2 over t. Okay, so this is our A, this is the same A, and this is our B. You see that?
Wouldn't the lower left element of B be 0?
Which one?
The negative 1 in your B matrix, shouldn't that be 0 because you've already accounted for it in A?
Okay, so it's gonna be minus x1. Yes, thank you. There. Okay. You're right. Okay, so now let's take a look at it. So what do we know? So the zero solution of this is uniformly stable. So let's take a look at 0, okay, T naught to infinity of BT. That is any T naught to infinity 2 over T dt, isn't it? Let's take the sum of all the absolute value. And that is 2 ln of t from T naught to infinity, and that is infinity. Remember, this is supposed to be E. Okay? So, really, the theorem, basically, the theorem doesn't tell us anything. The theorem tells us if this is uniformly stable and this is integrable, then you get uniform stability. So that we don't conclude anything about the theorem from the theorem. However, if we look at the solution, is two vectors. We have x1, x2 is sine t minus t cosine t and t sine t. And another solution, x1, x2 is cosine t plus sine t plus t sine t and t cosine t. And we will see that x, the absolute value of x, which is square root of x1 squared plus x2 squared, which is any solution, which is cosine square t or cosine t plus t sine t squared plus t cosine t squared, and that goes to infinity as t goes to infinity. So the solution is unbounded, and therefore the zero solution is unstable. So x equals 0 is unstable. So, okay. So this example shows the condition t0 to infinity of bt dt less or equal to e is necessary. Okay, it's necessary condition. Okay. All right, any questions? So basically, theorem 5.3.1 says nothing about example, whatever, about the example, because its conditions are not verified, are not satisfied, may I say. Okay? Any questions? So it's very delicate. Now, in order to know that this matrix is perturbed, perturbation matrix, if you look at the limit as t goes to infinity of the absolute value of the entries, you will get 2 over t goes to 0 at t goes to infinity. So you know this matrix is a small in t, but it's not integrable. Dwell on it for a second. Okay? Now, you may say, how did I find the solution? You can use a variation of parameters formula, correct? You could use a variation of parameters and find the solution. Okay? Any questions? So if you're interested in finding this solution, you say, how do I find the solution? Let me elaborate on it for a second. You can find the here you have x1 prime equal x1, x2 prime equal to minus x1. Okay? x1 prime, sorry, equal x2. Okay. Here's what I want to say. So we're solving x second plus x equals 0. So this has a solution, lambda squared plus 1 equals 0. So lambda equal plus or minus r. Correct? So what is the solution to that? So x of t equal to cosine t, correct? C1 cosine t plus sine t. Okay? So that is this one here. So you have, may I say, you have cosine t and sine t as solution. So this is a general solution. Cosine t, may I say, and sine t. Solution. All right. So what is our transformation? Our transformation was what? Can anybody tell me? x1 prime equal x2, x2 prime okay. So we had the substitution. Let's see. I'll get back with you. I'm just trying to help you out find the solution if you need to. So remember we took x1 equal to x and x2 equal x prime. Okay. So where did we get this solution from? So we have sine t and cosine t. So correct? So when x equal cosine t, that means x1 is cosine t and x2 equal to x prime, that is minus sine t. Okay? So phi is cosine t minus sine t. Now, let's take x1 equal to x and x2 equal to x prime. Now let's take x equals sine t. That means x1 is sine t and x2 is x prime, which is cosine t. Okay, so now we have sine t, cosine t. Okay, so this is your phi. All right. So what is the second solution of that? This one is phi of t, phi inverse of t naught, x naught, plus t naught to t is gonna be phi t, phi inverse of s. Okay? Okay? Times 0.002 over s ds. There you go. And if you do all this together, you will get what we got before. All right? In case you wonder where this came from. Now we know what phi t is. There it is. You find the inverse of it. The inverse is easy. So what is the determinant? The determinant is 1. The determinant is 1, correct? So you can invert the matrix immediately, okay? And so the determinant of phi is 1. Phi inverse of s is 1 over 1 times dA cosine t, cosine t, do you still remember the inverse of the matrix? It's dA minus B minus C. dA minus B minus sine t, sine t. And this is supposed to be S. Okay? There you go. So now you do phi t, phi inverse of S times all these together, and you integrate them, and you will get the solution we got. Okay? So there we go. All right. Any questions? I think I spent more than enough time on this. Okay? Any questions? All right.
Looks like James put a question in the chat, Professor.
Yeah, let me take a look at it. Suppose you are given a non-constant A matrix, but you could break it into a constant matrix and a non-constant matrix. Could you use this theorem to determine stability? Yes, as long as this one is integrable. You see that? He's asking a good question. He's saying if you have a non-constant matrix A, can you split it into a constant plus non-constant matrix like this? Yes, but remember that condition on BS, DS has to be finite, okay? In order to get anything out of it. All right, did I answer your questions? All right, good. Okay, let's move on. So, now we're gonna take a look at theorem 5.32. Assume the zero solution of 5.31 is uniformly asymptotically stable. Okay? Then, and then we're gonna all right. Suppose T0 to infinity bt dt less or equal to gamma t minus t naught plus beta, or t bigger or equal to t naught bigger or equal to 0, and this is 5.3.5 for positive constant gamma and beta. Then the zero solution of 5.32 is uniformly asymptotically stable, provided gamma less than epsilon over k, where k is given by phi of t, phi inverse of s, less or equal to k e to the minus epsilon t minus s for t bigger or equal to s bigger or equal to 0. Okay? Where k, may I say, and c are given by this. Now, where did this come from? Can you tell me where did this come from? This condition?
I think it was an earlier theorem. I don't know which one.
Yeah, you remember? What are we assuming? We're assuming the zero solution of 5.21 is uniformly asymptotically stable, right? That means this one must hold, correct? You see what I mean? This is where it's coming from. All right. Well, proof, since x equals 0 of 5.3.1 is uniformly asymptotically stable, the star must hold. Okay? You see what I mean? Now let us use the variation of parameters formula. Again, let X be the solution of 5.3.2. Then xt equal phi t, phi inverse of s x naught plus t0 to t, phi t, phi inverse to s, bs, x of s, ds. Okay? All right. Any questions? Um, here we missed something. What did we miss? We missed the XS. No, it's okay. Because I assumed it is 1, 1, so it's all right. XT equal to all right. So here you got the X naught. You're gonna get 1. Here I missed. For example, this will be one solution. This will be one solution. And then you will have here XS. XS could be the cosine S minus sine S ds. Okay? You gotta multiply all these together. All right? Yeah, I missed this one here. And then this will give you one of those. Will give you one of those. Then to obtain the other one, you will use this one, okay, as your solution. Then you will use it here, and you'll get the second solution. Sorry about that. Now, the reason is because there is an X here. You see what I mean? With the variation of parameters formula. That's what triggered what I missed before. All right. Any questions? All right. So what we're gonna do now, we're gonna take the norm. This will be less or equal to k e to the minus ct minus s x naught. By the way, in the book, again, there is a typo. At the end of the theorem, the statement on page 138, this should be e to the minus psi. But the proof is correct later on. I just a typo. Sorry again. Just break my heart. So we have this one. Oh, this is, sorry, this is T naught. And so this will be T minus T naught. S will be here. Okay? Plus K T naught to T E to minus of C T minus S ds x of s ds. Okay? Are you with me? Now, in order to use Gronwall's inequality, I need to have, you see here, I have this term. I need to lump this with this. And this x supposed to be the same. So what I am going to do, I'm gonna flip the board on you in a second. Okay? So we're gonna multiply both sides by e to the c t minus t naught. And I'm talking about this one here. So we're gonna get x of t e to the c t minus t naught less or equal to x naught. There's nothing left because this is the opposite sign of the term here. Okay, you remember what x of t is. Less or equal to e to the minus of c t minus t naught x naught plus k. K t naught to t e to the minus of c t minus s ds xs. So this is what we have. So I am multiplying by this. So this is gonna be a plus t naught to t k times e to the minus of c t minus s, right? A plus or minus t minus t naught times bs xs ds, because I need to factor this. Okay? So this is equal to x naught plus t naught to t k. And then I'm gonna have e to the minus of c. What am I gonna have? T and t go away. I'm gonna have minus s plus t naught. So it will be s minus t naught, right? You see what happened? Times bs xs ds. Well, now we have a condition on BS. What is the condition on BS? We did erase it, of course. It was here. The condition on BS was, oh, this is toward the end. That's okay. All right. So what I am going to let yt equal xt e to the psi t minus t naught. Then this becomes yt less or equal to x naught plus t naught to t k bs y of s ds. Now I can use the Grunwald's inequality. I got y, I got y. So this is u, this is my v, and this is my u. You see what happened? Take a look at it in a second. Okay. So by Grunwald's inequality, we have y of t less or equal to x naught e to the t naught to t k bs ds. Okay. And this is less or equal to x naught e to the k t naught to infinity bt dt, and this is less or equal to x naught e to the k. What is this condition here? You see how it pulls out? Okay. So this is less or equal to x naught k, then it's gonna be times gamma t minus t naught plus beta. You see what happened? But look what we had. We had this. So we have xt e to the psi t minus t naught less or equal to x naught e to the k of gamma t minus t naught plus beta, or xt less or equal to x naught e to the k gamma t minus t naught plus beta minus psi t minus t naught. I multiply by the inverse of that. Okay? And this is less or equal to e to the k beta times e to k, no, k, e to the t minus t naught. All right? I took the k beta out. E to the t minus t naught. Now, if I factor this, will be times gamma minus psi. What do you think? Maybe I want, so let's see how am I doing it. And I do have k here. Yeah, t minus t naught times gamma minus psi. So what do we know about, so we have this one now. What do we know about, we need to go back to the theorem, to the gamma less than psi over k. Okay? So this is x naught e to the k beta times e to the k of gamma minus psi over k times t minus t naught. Oh, uh, let's see. Here, I have the k in front of the t minus t naught. And it's not in front of the psi. So I'm gonna do this as k gamma. K gamma t minus t naught minus psi. Okay? So if I factor k out, I got k gamma minus psi. So that is perfect. You see what I have? Now, any questions so far? I want to continue with the proof for you. It's a little bit complicated, but you will never see such a proof in your lifetime again. This is it. I am not done yet. Okay. Can I flip the board for a second? See if there's any questions. Okay, there is one question. But the yt in the integral has minus xi, and yt is defined as a positive. No, I think I answered the question. I answered the question here. Let's say where. Okay, so what do I have here? T naught minus S and e to the minus. Let's see where. Somebody is asking questions. Okay, so T naught minus S. It should not cause any issues. Oh. Oh, sorry. I think now I had it correct. There. So here I have S, so I can pull this out. So minus S plus T naught. So this would be e to the psi S minus T naught. Sorry about that. So everything is correct. Thank you for the question. Everything should be fine. After you substitute, everything should fall into place. So this should be like this: psi S minus T naught. Okay. And then because we're replacing these values together. All right. So this is a typo. So it should be, it follows. If you look at it, T minus T go away. So you have a plus sub CS, you got a plus sub CS, and you have minus, minus, so you have a plus T0 minus, minus T0. Perfect. Okay, thank you. Yes, it matters. The answer to your question, yes, it matters. It has to line up perfectly. All right. Okay. We're almost done. I think that will take us to the end of the, hopefully not. All right. Since gamma less than C over K, there is an alpha positive, so that hence from here x of t less or equal to x naught. Okay. E to the k beta times. Now, remember, we have k gamma minus c, or gamma minus equal to minus alpha e to the minus alpha t minus t naught. There we go. So this is what we should have. Why? Because gamma minus ck less or equal to minus alpha, minus K alpha. There. Okay. All right. Now we need to argue for stability. Okay. So what do we need to argue for stability? Can you go ahead and figure this out? See how would you do stability? Uniform stability. We just did it a little bit ago. Sorry about that. Okay. All right. So let epsilon positive. We must find delta positive so that if x0 less than delta implies xt less or equal to, from here is delta e to the k beta, correct? All this is less than 1. This is less than 1. And let me call this is double star. So this will be equal to epsilon if delta is epsilon of e to the k beta. So x equals 0 is uniformly stable. Now we need to show it's uniformly asymptotically stable. Okay? Remember, why don't you read the definition, go back and look at the definition of uniform asymptotic stability. Okay? Take a look at it. So from the uniform stability, let gamma equal to delta equal to 1. Thus, for x0, less than 1, we want x of t is less than u for t minus t naught for t bigger or equal to t naught plus t mu. Okay? So let's go back to 2 star. So we have x of t less or equal to 1 times e to the minus k alpha t minus t naught. We want this is less than mu for t bigger or equal to t naught plus t mu. So what is this t mu? So this mean e to the minus k alpha t minus t naught less than mu, correct? Solve. Take exponential on both sides. That means 1 over k alpha t minus t naught is less than ln of mu. Okay? Okay, is that correct? Let's see. No. So if, let me, I'm bad in algebra today. So let me do it here for you. So this is what we want. We want this one to be less than mu. And, oh, what happened to my k beta? Okay, let's go back to so what was the can anybody read for me double star? So was it xt less or equal to x naught e to the k beta times e to the minus alpha k t minus t naught? Is that what we had? Can you confirm? Okay. So we're taking delta to be 1, so this is less or equal to e to the k beta. Let's see if anybody said anything. And then I want e to the minus alpha k t minus t naught to be less than mu. So we need to solve for divide by e to the minus k mu. Okay, so this is let's divide by e to the k mu if you like. So e to the minus alpha k t minus t naught less than mu e to the negative k beta. Okay. This means this means 1 over e to the alpha k t minus t naught less than mu e to the minus kb k beta. Okay. All right. So that means 1 over e to the alpha k t mu less than mu e to the minus k beta. You see what happened? Because what do we have? We have this one. If t minus t naught bigger than that, then this is gonna be. So now take logarithm on both sides. We have e to the alpha k minus e to the alpha k, sorry, take ln on both sides. So we have ln of 1 minus ln of e to the alpha k times t mu is less than mu e to the minus kb. So that this is 0, okay? And then this is ln of e to the alpha k t mu is bigger than minus mu e to the minus k beta. All right? Oh, I need ln here. Ln, less than this ln. So bigger than minus ln. All right? And this is an exponential, so we have alpha k t mu is bigger than minus ln of mu e to the minus k beta. Oh boy. We're almost done. So hence, for t mu bigger than 1 over alpha k of ln of mu over e to the k beta, we have xt less than mu for t minus t naught bigger or equal to t mu. There we go. I have minus, sorry. There we go. Okay. And here I used one of the theorem. So, all right. So that does it. It's a very long theorem, tedious theorem. The proof is, but there we go. We found it. Okay. And remember, you say this is negative, but you see this one, mu is small. E to the k beta, mu is less than 1, and then divided by a number that is bigger than 1. So this number is between 0 and 1, and the logarithm of it is negative times negative, you'll get a positive. Okay? That's why this is how you determine the t mu. Okay. Any questions? All right. All right. I'm going to stop here if you don't have any questions. It's been a good, tedious lecture. And I did assign homework last week, so be careful to take a look at it. I may assign another one maybe tomorrow or Wednesday. All right. Have a good day if you
don't
Yeah.
see any homework on there. There was the one due Friday, but I don't think there's another. Yeah, nothing else is showing up. There's only 3 homeworks listed.
Really? All right. Let me take a look at it. Let me see. Stay with me. Canvas. It's amazing. Assignment. Homework 4. Oh, I did not assign it. Due June 11. If you need more time, I can. Okay, let me. No. Okay, so you should be able to see it now. Sorry again, stupid. It's always me. All right. So let me see. I'm going to extend the deadline. The due date is June 14. Okay. So I extended the deadline. Okay. And it should be published. All right. Sorry about that. Back to Zoom.
Okay, can confirm it came through.
Uh, it shows up now.
Yep, I can see it now.
Thank you.